In this section we examine a curious situation that occurs in a right triangle when you draw the altitude to the hypotenuse. Before we can get to that though, we need to go over a new type of average, the geometric mean. You were likely introduced to the concept of average of two or more numbers in grade school. Simple idea, not too tricky. Later on, they likely told you that the more mathy and official name for average is the mean. Some of you may have had some pretty militant teachers, too, that insisted that you call it mean and that its nickname average is just no longer kosher. In any case, what they probably didn't say, yes, even the militant ones, is that the mean isn't even the full name. If you just say mean, then you are referring to the arithmetic mean. It's like you are meeting arithmetic mean for the first time and it says, "Hi, my name is arithmetic mean, but you can just call me mean." Many of you have probably seen a situation like that before. In any case, no matter what you refer to it as, the concept of arithmetic mean isn't hard. If you take the average, arithmetic mean, whatever you want to call it, of 2 and 8, then you simply add the two of them together and then divide the result by 2 to get 5. If you take the average of 3 numbers, you add them all up and divide by 3. In general, you just add up all the numbers you want and then divide it by the number of terms that you have. This should all be review, but we need to get arithmetic mean fresh in your heads as we shift to the new idea of geometric mean. There are no AKAs with geometric mean. You generally refer to it by its full name. Clearly, we need to go over the difference between arithmetic mean and geometric mean. When you find the arithmetic mean, say of 4 and 9, then you are finding the number exactly in the middle of those two numbers. With geometric mean, it is another way of finding a number in between two given numbers. But the method of getting there is different. I could go into the details about how geometric mean is good about normalizing two different types of numbers, but that isn't necessary for you now. All you need to know is that geometric mean also finds a number in the middle ground between two numbers, and that this geometric mean often shows up when dealing with shapes, which is how it will end up coming up in geometry pretty often. For example, let's say I have a rectangle and a square, which both have the same areas. Here this rectangle and this square both have an area of 36 units squared. The base and height of the rectangle are 4 and 9, just like in my arithmetic mean example above. The side length of the square, 6, happens to be the geometric mean between 4 and 9. This geometric mean just seems to constantly show up when shapes are involved. The 6 is a number somewhat in the middle of 4 and 9. With arithmetic mean, we know that the exact middle is 6.5. You will find that the geometric mean often ends up just a little bit smaller than the arithmetic mean. Here, the geometric mean is 6, just a little smaller than the arithmetic mean. That was an example of geometric mean showing up, but now it's time for the actual definition. The geometric mean of a and b is the value x that satisfies the proportion a over x is equal to x over b. There is the restriction that x, a, and b are all positive numbers, which is fine, especially in geometry where we don't deal with negative distances and such. So if we wanted to find the geometric mean between 8 and 32, we set up the proportion 8 over x is equal to x over 32. That geometric mean shows up twice in one of the diagonals. Now we just cross multiply and solve. Therefore, 16 is the geometric mean between 8 and 32. That is how we would solve it with the official definition. And if you like setting up that proportion, then great. However, let's work through another way of doing it. Here we have the official definition again. So let's start with that proportion. If we are solving for x, we will start by cross multiplying, and we end up with x squared is equal to ab. Then we take the square root of both sides, since we're solving for x, and end up with x equals the square root of ab. So to find the geometric mean x, you simply multiply the two numbers together and find the square root. This is the summary of the two different types of mean. The first one should be familiar. You add the two numbers together and divide by 2. The new type, geometric mean, you multiply them together instead of add, and then take the square root. If you like the official definition better, by all means set up that proportion instead. Note, there is one common error with geometric mean. Students will often remember that they need to multiply instead of add, but then they forget what the heck comes next. So they just divide by 2, just like arithmetic mean, for lack of something better to do. That's not right. Don't do this. You take the square root. You don't divide by 2. Here we have right triangle ABC. Simple enough, right? Something interesting, weird, and or cool happens to this right triangle when you draw in the altitude to the hypotenuse. The hypotenuse is always the side opposite the right angle, so let's draw in that altitude to the hypotenuse. Something curious happened by doing that. First, realize that there are now 3 triangles. I'll split them out so they are easier to see. We started with triangle ABC, and then we now also have triangle ADB and triangle BDC. The weird thing, though, is that all 3 of those triangles are similar to each other. Personally, I found that a fascinating little trick, but then again, I am a math nerd. It happens any time a right triangle has an altitude drawn to its hypotenuse. Very interesting, at least to me. Now we get to the 3 related geometric means. The fact that drawing the altitude to the hypotenuse creates 3 similar triangles is interesting, but those similar triangles lead directly to, and are the reason why, 3 geometric means pop up. And that is what we will be focusing on now. This is what will get you to use those geometric means we worked on at the beginning. Before showing you the 3 geometric means, you need to focus on 2 things here. Drawing in the altitude segments off the hypotenuse. We still always have the full hypotenuse, line segment AC, but the altitude we drew in splits the hypotenuse into 2 pieces. On the left side we have line segment AD. On the right side we have line segment DC. Understand that we have 3 hypotenuse pieces. In our picture, we also have 3 non-hypotenuse line segments. We have line segment AB, there is line segment BD, and finally we have line segment BC. These are the 2 groups of pieces that you should have at the forefront of your mind as I move into describing the 3 geometric means that we have. Each one of the lengths in the non-hypotenuse group is a geometric mean between 2 pieces of the hypotenuse group. The first geometric mean is AB. AB is the geometric mean of the piece of the hypotenuse it touches, AD, and the whole hypotenuse, AC. Remember I told you that each geometric mean we are covering is the geometric mean of 2 pieces of the hypotenuse, or the whole hypotenuse. Here it is the whole hypotenuse, and the piece of the hypotenuse it touches. Note that the other piece of the hypotenuse, DC, is not involved. It doesn't actually touch AB, and the other 2 parts do. So that is another way to help you remember which pieces to use. If you are solving a problem using this geometric mean, you have 2 options. You can use the formal definition, or some of you will opt to do this instead. Once you get to the formula, you are home free. The hardest part is remembering which pieces to use in the formula. The second geometric mean is BC. It is the piece that splits the hypotenuse into pieces in the first place. It is the geometric mean between the 2 pieces of the hypotenuse that it created, AD and DC. Once again, you have 2 options for how you set up your formula. Take your pick for which one you like best. Finally, we have the last geometric mean, BC. BC is the geometric mean of the piece of the hypotenuse it touches, DC, and the whole hypotenuse, AC. Once again, the piece of the hypotenuse that it doesn't touch, AD, is not involved. Hopefully that helps you remember which pieces to use when you plug those into one of the 2 formulas that you can use. That's all for this section.